Good morning, good afternoon, and good evening, everyone. Wherever you are, I hope you are safe and healthy. My name is Pradeep Parameshwaran. I'm the Security and Compliance Lead for LinuxONE and LinuxONE IBM Z. I'm based out in IBM Research Lab in Germany, which is situated in a small city called Böblingen. Probably everyone knows Böblingen by the name of Stuttgart, which is the home for Porsche and Mercedes. I'm here to talk about a 360-degree view on LinuxONE security and compliance. There's a standard disclaimer as from the IBM part. So this is the agenda which we'll be focused on. It's like a cycle here, so that's why it's called a 360-degree view. So we will start with some introduction of the security capabilities around Z15 and LinuxONE, and we will jump into the secure execution technology. We'll briefly touch base on pervasive encryption and fully homomorphic encryption before explaining hyperprotect virtual servers. Finally, we will have an ease of use compliance aspect, which wraps up the whole story around the compliance and security. So IBM Z15 and LinuxONE had brought up with a lot of security capabilities over the course of the year. The security capabilities are either built into the platform or we rely a lot on the Linux open source ecosystem as well. So let's talk about both here. First, the platform level part. We have tight integration to the hardware crypto accelerators, especially Crypto Express 7 cards, which got released with Z15 and LinuxONE 3. Crypto Express cards are our hardware security modules. And then in addition, we also have a crypto accelerator, which is actually situated on every core of the CPU. This is used for high speed and bulk symmetric encryption, and we call it as CPACF. In addition to the hardware accelerators, we also focus a lot on workload isolation. So the workload isolation in case of LinuxONE is actually EAL 5 plus certified with our standard LPAR technology. And the isolation is also for virtualization. Then in the recent months, we had also released two new offerings. One is IBM HyperProtect Virtual Servers, which is focused on securely building, deploying, and managing a workload on a hybrid cloud environment. The good thing here is the virtual servers cannot be accessed by a cloud administrator. We also brought in a technology called protected virtualization or else secure execution. This is a hardware-based technology where we can basically run a trusted workload on an untrusted environment. So that is called as the trusted execution environment. Why this is done? To avoid the insider threats and external attacks. So as you can see from this chart, we rely both on the open source and also on the platform-specific capabilities. And we'll explain in detail in our charts now. So first, let's start with secure execution, otherwise called as protected virtualization. So data security is something which is not an option anymore. The reason is there is a lot of money which is being given as a cost for the insider threat. And as you can see from the percentage here, insider threat is really a challenge now because it's the root for 60% of the cyber threat attacks. And on the left side, you also see a lot of fines which are being given to the companies by the regulatory bodies. So the message is data security is not an option anymore. And what IBM had done is they leveraged the open source technology together with the platform specific technologies to bring in secure execution for Linux. Otherwise, our own trusted execution environment. So what does this mean? Let's look at this picture here. So we have an LPAR, which is actually hosting a KVM. And the KVM has a KVM guest, which can be a Linux workload here. And then basically this particular workload can be running with secure execution enabled, and the host KVM cannot access the data which this guest is actually handling. That's good, right? What this avoids actually? Two things. One is basically the administrator of the KVM cannot access the memory of the KVM guest which is running. That's good. And the other thing is the neighboring KVM guest also cannot bring any of the malicious workload and then get into the host to the next guest. That is not possible because here the scope or the trusted execution is actually around the KVM guest workload itself. So how this is done? We relied a lot on our own hardware-based security technology, and then we relied a lot to enable this via the KVM. Now let's take it into a context here. So how these access restrictions are getting hardened. Let's look at today's challenge first. So in today's challenge, we have the LPAR, we have the KVM hypervisor, and we do have multiple guests which are running. All these guests are isolated vertically, but then the guest memory can be accessed by the Linux kernel here, as you can see from my arrow here. So what it means exactly is there is no isolation between the host and the guest. And this is a problem because this is actually a space for the insider threat. Now, let's look at secure execution. With secure execution, we have a fully isolated and protected hypervisor, which is actually isolated both on the vertical and also on the host level. So the hypervisor admins, they can basically deploy the workloads, but they don't have any clue what is the data hosted in it. And then they can also have multiple isolated KVM guests. And if one is malicious, it can break down into the Linux kernel, but it cannot go into the next guest, which is just having the secure execution enabled. So that is kind of the cool thing with secure execution. And as you can see here, it's a simplified implementation via the KVM. Now, let's look at real-time example. Let's assume there are three different services which you want to run both horizontally and vertically isolated, like you can see here from blockchain, SecureDB, and crypto services. In a normal world, what happens is without secure execution, you need to obviously dedicate your LPAR to each and every one so that you have full isolation. But with the secure execution enabled, you can basically run it on a single virtual server and still have it isolated both across the vertical and horizontal here. This is a perfect multi-cloud or multi-tenant cloud environment, right? So that's all about secure execution. The next topic we are going to discuss about is privacy encryption. Over the journey of the privacy encryption for the last years, IBM Z was heavily focused on data at rest and data at flight encryption on the aspects of privacy encryption. For this particular session, we will just reduce our scope to the data at rest encryption. Before we talk about privacy encryption, I think it's better to understand the hardware crypto support on Z15 and LinuxONE. We talked a lot about crypto express adapters already. To manage the crypto adapters, we have something called trusted key entry, you can see here. And the trusted key entry also has a workstation, which we call as TKE workstation. And how do you authenticate all these workstations? You use a smart card. So you can see how secure the key management process is. And then one more thing is our Z crypto stack, which is actually a unique crypto stack, is also relying heavily on the Linux crypto stack, like standard Linux kernel crypto stack. As you can see, there are some hardware enablements done, which is done as a part of the platform enablement. And then we rely a lot on the Linux kernel modules like Dm-crypt, for example, or we also have our own zcrypt device driver. And also we also exploit the standard libraries like OpenSSL, libcrypto, and OpenCryptoKey, for example. But everywhere we also rely or we also exploit all the Z specific capabilities so that we can take the equal balance between security and whatever the open source community provides to us. So on the privacy encryption part, let's focus specifically on the protected keys. Protected keys are nothing but these are wrapped keys which are generated by the master keys, and these master keys are basically hidden on a LPAR or a guest. So what this means exactly is each virtual server will have its own master key and be hidden. Basically, it's not accessible by the operating system. And then these protected keys can be used for all the symmetric encryption. You can see obviously the pros here are there are no clear keys in the operating system memory. And then you basically rely a lot on the CPACF for encryption decryption, which is very fast. But there's also cons, right? I mean, hiding the master key is not good as hiding it inside a HSM module, right? Like for example, our HSM modules are like FIPS 140-2 certified, level 4 certified, so it's tamper proof. So hiding there would be really great, right? So let's look at the how to generate a protected key. So generate a protected key first, you need a secure key, which we need to generate from the crypto adapter cards. And then what you need to do is we need to use the pass module to transform the secure key into a protected key. And the pass module will take care of the job of negotiating the keys with the CPU and the firmware. And then we basically use the protected keys for all our operations. So let's put it in a real world perspective, and let's take Dm-crypt as an example. Dm-crypt is actually used for the end-to-end data at rest encryption. What does Dm-crypt exactly does? It's a mechanism to actually do the end-to-end data encryption, and then the data is only available in clear in the application level. And basically what happens is you encrypt your whole device, your whole block device, and then whenever you write something, it's encrypted, and when you read it from the application level, it's decrypted. So let's take a look at a scenario where how Dm-crypt is handling both the plain format and looks-to format. So basically, in a plain format, if you want to encrypt it first, you need to open the device, and then you encrypt it, and then you mount it, and then you basically read and write. In a looks format, what happens is you create the looks header by doing a format with the AES keys and the passphrase. So these both are then written as a part of the header. And then basically when you open it, you just need to issue the passphrase, you mount the device, and you read and write. But do you see a problem? Well, I had listed here in red colors, right? So in a plain format, it's always challenging to associate the volumes with the keys and ciphers. And how do you securely store the AES key? And the same challenge comes in looks2 format as well, because basically you have the same problem here. The only bad thing is you also need to securely store your passphrases now. So let's see how protected key helps here. So with the protected key, you basically in a plain format, you generate a secure key and you use pass module to create a protected key AES cipher. Now you use that to open the volume and mount it, read and write. So basically you don't have the pain to securely store the key somewhere because it's already protected and secure key here. Now let's take a look at the looks format. With looks format, basically you have the secure key and then you have the protected key with the passphrase, which is actually written as a part of the looks2 header. Now here, passphrase is nothing but an checklist, to be honest, because all you need the passphrase is to open the volume, but the passphrase does not have any sense here because we rely heavily on the protected key here. So you can obviously have a password like 123, for example, because having just a password doesn't make sense because you need the protected keys. So that's how the Dm-crypt volume management is done with protected keys. And that's one of the extensions for the privacy encryption. Now, let's focus on the next technology, which is fully homomorphic encryption. So, in this afternoon, you will have one more session from Flavio and Eli, who are the FHE experts, who will talk about the fully homomorphic encryption. All I'm trying to say here is fully homomorphic encryption is a technology which is currently being exploited in IBM Z15 and LinuxONE. So this is invented on IBM Research, and we do have an open source project called HIPPA. So what exactly is homomorphic encryption technology? Whenever we explain math, it's always difficult. So let me try to be a bit simple here. Homomorphic encryption means you basically work on an encrypted data for all your processing and computation. So what it means exactly is you can encrypt your data, you can take it to an untrusted environment and do all your computations. For example, you can have your data in the on-prem, you can encrypt it and send it to your cloud offering, which actually does not care about the clear data. All it does is to process against the encrypted data itself. So in IBM, we released something called toolkits, which is actually a set of development experience environment where you can build use cases with the fully homomorphic encryption. And these toolkits are, by the way, available on LinuxONE Z as well. You can obviously go and give it a try by downloading the toolkit from GitHub. And whenever you're struggling with the use cases around FHE, you can obviously rely on our tips here. We actually have some examples of data privacy already as part of the toolkit, but there are multiple exploration areas which you can obviously rely on. I hope that gives a good insight on the FHE now. And obviously, please listen to the session from Flavio and Eli. And then final security offering, which I want to focus on, is HyperProtect Virtual Servers. HyperProtect Virtual Server relies heavily on the value proposition of how an insider threat can be avoided and how you can do a secure build and deployment of a workload. So there are multiple stages involved here where you build a workload and then you deploy it with trust. And by the way, it's all backed by our crypto cards. Let's look at a deeper dive into the architecture here. The HyperProtect Virtual Server relies a lot on Secure Service Container Alpha. So that is actually a lockdown appliance, which is basically cannot be accessed by the administrator directly. I mean, you need an REST API to do it. And that's an insider threat mitigation then. And one more thing is, secure service container with hyperprotect virtual server relies a lot on Docker interfaces. And what you ultimately do is, from a customer standpoint, all you need to bring is a Docker file, which actually is capable of building a Docker image. You pass that Docker file to the secure build process, and the secure build process builds the image, signs it, and then deploys it to the hyperprotect virtual server. By the way, each image will fit into only the specific virtual server where it's supposed to be deployed. And then basically you also have a lot of management options to manage these images using a CLI interface. As you can see here, this is the application which got deployed, and then you have the secure build process to deploy that application, and also you have grep 11 interface where you can exploit and crypto capabilities. And there is also monitoring components available to check the status of your app. So there is one unique thing which you have noticed already here. We don't really run this container as a run C container. We run it as a run queue container. It's a project open source by IBM, and run queue relies on a small KVM instance, and inside that KVM, you basically run your Docker images. So in this way, you're isolated vertically, and also you're isolated horizontally with the secure service container technology. I hope that gives a good insight on the hyperprotect virtual server. Now let's move to the ease of use compliance aspects. So compliance is becoming a big like additional overhead for the enterprises. And there's a reason actually. I looked into the recent data breaches which came in 2018, 19, and 2020. As you can see, there is one common here: human error. Customers tend to accept the defaults which the vendor provides. And the customers don't care about the hardening of the environment itself. And these are main factors for such a breach actually. It's not that the vendor is kind of, not satisfying the compliance part. It's more about how you continuously keep that compliance going. And on this level, let's focus first on the system hardening, because that's the basic for the compliance. Once you have the hardened system, you basically have a secured environment, which actually means you are compliant. So the hardening can be on multiple levels. It can be on a base layer, which is like, bootloader hardening, or even it could be a PAM module hardening. It could be on the kernel level where you harden your file system, or you can also harden your compiler. So combined with all these things, you'll basically generate a hardened system, which is actually, secure and fine. So when I talk about hardening, there is always multiple areas to focus on, starting from access control till intrusion detection, for example. In access control can mean anything. It can mean SE Linux, or it could be like a user access control where you rely on an LDAP. So every time when you have a focus area, please focus on all these building blocks. Please make sure that your SE Linux is enabled. Please make sure your PAM modules are properly configured. Please make sure that your IP tables or NF tables have proper firewall rules in place. Please make sure that your AID is enabled for file integrity monitoring. Not just enabled, please make sure that you're actually configuring your AID database to actually track the important files you need to track. Okay, so in this way, what I'm trying to represent here is the focus area and what are the building blocks which need to be hardened on that. And again, it's not just the focus area does not end with a single slide. For the secure networks as well, you have OpenSSH, you have OpenSSL. Make sure that you are actually using the proper options on OpenSSH, for example, in the SSD config file. And then make sure that your OpenSSL is actually using the crypto capabilities from the Z. And then if you talk about secure data at rest, for Dm-crypt, rely on protected keys instead of relying on clear keys. And for compliance check, rely on OpenSCAP, for example, which I'll briefly touch on in the next slide. So in this way, it's all like there are a lot of focus areas. There are equally building blocks on that. So finally, OpenSCAP. So we saw some of the building blocks, right? So now let's see how to evaluate all these building blocks or how to evaluate the gaps. So here OpenSCAP helps us. OpenSCAP is an ecosystem which actually provides a way to manage your system configuration from a compliance standpoint. And the good thing is it also remediates it. So basically it's built by Red Hat and maintained by Red Hat as an open source project. And we verified it on Z as well, on LinuxONE Z as well. And OpenSCAP, the SCAP protocol is actually NIST certified, It also contains multiple regulatory and compliance policies which you can scan against. So here's one example with OpenSCAP. So OpenSCAP hardening for zIPL here. So zIPL bootloader, as you know, it's a Z-specific bootloader. And basically what we did is we extended the OpenSCAP profile to look for these settings as well. As you can see on the left-hand side here, we should make sure that the zIPL bootloader config does not disable Linux by default. In the same way, we also said what is the reason for that. Okay, so why this should not be done. And then in the same way, we also tried to evaluate a rule where we need to make sure that the auditing starts prior to the audit daemon is started. So that configuration can be done on zIPL, where we set this flag called auditable, right? So in this way, what we are trying to do is we are trying to incorporate these specific recommendations into the OpenSCAP profile as well. So with this, I'm almost end to with my presentation. So we covered the security capabilities on LinuxONE here with a strong emphasis on the open source ecosystem. And then we talked a little bit about the regulatory requirements and how the multiple security blocks or the building blocks are fitting into the context. And we saw some tooling around the regulatory requirements as well, like OpenSCAP, for example. I did leave some references as a part of the session here, which you can basically later look at. There is one red book which is focused on securing your cloud on LinuxONE, for example. And that ends my session. Thank you very much for listening. I'm looking forward for the live Q&A. Thank you very much.